Hello everyone, welcome to the webinar for Vitis Data Center Acceleration Flow. In this webinar, I will explain how to use the GT Kernels on Alveo Data Center Accelerator cards to implement the inter-card communications. There will be 4 parts here. First, we will take a quick look at the functions of the GT Kernels on Alveo Data Center Accelerator cards. Second, I will introduce the Vitis Flow to implement Aurora interface on Alveo with GT Kernels in details. Then I will briefly introduce the Vitis Flow to implement Ethernet interface on Alveo with GT Kernels. Finally, some key points are given as a summary. GT kernels are high-speed SerDes in transceiver IPs for high-throughput communication. If you are not already familiar with GT kernels on Alveo card, let's take a quick look. As you may have known, current Alveo data center accelerator cards are based on the UltraScale Plus FPGA. A lot of GTY transceiver I/O ports are integrated in these FPGAs. The Versal devices for VCK5000 accelerator cards have similar features. The GTY transceiver is a high-speed SerDes interface providing the low jitter required for demanding optical or copper interconnects. The GTY transceiver supports multiple protocols, and the 4 bidirectional channels are grouped in a primitive. The peak line rate for GTY transceiver is 32.75 gigabits per second. With the GTY transceivers, the user could implement high-speed communication ports on Alveo card easily. As you may have noticed, most Alveo cards provide 1 or 2 QSFP28 interfaces, which are bounded to the GTY transceivers of the FPGA. The QSFP caches on Alveo support the 25 gigabits per second QSFP28 modules and back compatible to the 10 gigabits per second QSFP Plus modules. Both copper and fiber cables can be used according to the various distance requirements. The user can implement Aurora, Ethernet, or other communication protocol using the GT kernels and the QSFP28 interfaces on the Alveo cards. Now I will briefly introduce the Vitis Flow to integrate the GTY transceiver on Alveo card to implement the Aurora communication protocol. An example design is provided here to illustrate the design flow, and you can find the source code on the GitHub repository of the Vitis tutorials. Please note, if you want to run the design on Alveo card, you will need a QSFP loopback module, which could be inserted into the QSFP cache of the Alveo cards. Let's start with Aurora protocol. Aurora is a lightweight, high-performance, point-to-point communication protocol. You could consider it a highly simplified version of the Ethernet standard. An only PHY layer is defined, which includes the physical coding sublayer and the physical media attachment sublayer. Aurora protocol uses the high-efficient 64-66 encoding to provide high-throughput communication with flow control, and is very flexible in the channel configuration for various scenarios. You can implement unidirectional or bidirectional communication with the different channel number configurations. In general cases, the data center computing loads often require a large number of computing resources that cannot be accomplished with a single Alveo card. Instead of distributing and coordinating the workload via the PCI Express and Ethernet with multiple Alveo cards, we can implement the lightweight intercard Aurora protocol communication on every card directly. This greatly reduced the system latency and improved performance. The workload distribution strategy is very flexible. For example, we can separate the whole workload into identical pieces and dispatch them to multiple Alveo cards. We can also put a different stage of computing into different Alveo cards to form a pipeline-style processing flow. For Alveo cards with one QSFP port, such as the U50, we could implement direct point-to-point link to connect two cards with Aurora. For those cards with two QSFP ports, such as the U55C, we could implement a ring to connect multiple cards with Aurora. Xilinx has provided the Material Aurora IP for the users, and it is totally free of charge. The Aurora IP is very easy to use. It provides native or access slave interface for IP behavior control and status feedback, and it uses standard access stream interface for data transfer. Generally, the Aurora IP supports up to 16 lanes, and for Alveo card, it can provide up to 4 lanes and over 100 gigabit per second throughput for one QSFP port on Alveo cards. Aurora IP supports frame mode and stream mode for different data transfer styles, and example designs are also provided in Vivado for users' reference. Now let's look at the example design. The design implements a QSFP port loopback test with the Aurora protocol. It uses the 4 Aurora channels to realize the 40 gigabit per second transfer speed. It includes 3 Vitis kernels, an RTL kernel integrating the Aurora IP and the data FIFO IPs, an HRS kernel to send data to the Aurora kernel via access stream port, and another HRS kernel to receive the data from the Aurora kernel. The transmitted data is generated by the CPU and put into the global memory of the card. Then the data will be sent out via the Aurora IP and received back by the Aurora IP itself. Finally, the received data will be compared with the transmitted data for verifications. Here is the full design flow. First, we use Vivado to generate the core Aurora IP, finish the top RTL wrapper design, and package the top design into a Vivado IP and convert it to a Vitis kernel file. The remaining flow is basically same as the standard Vitis-based acceleration applications. We just generate other Vitis kernel files, finish the integration with the Vitis and the Alveo platform, then finally get the Excel bin files. In Vivado, you can generate the Aurora IP with GUI or command line interface. To explain the IP configuration options clearly, we use GUI with the Alveo U200 as a target hardware here. Here is the major options you may want to modify. First is the line rate. In the design, we use the default 10.3125 gigabits per second. The next option is the lane numbers. You can select the lane number between 1 to 4, since we will use only one QSFP interface here. In case you may want to use 2 QSFP ports to form a single Aurora link, you can set the lane number up to 8. Please note, each Aurora lane needs 64 bits access stream data bus, so if you use 4 Aurora lanes here, a 256-bit access stream port is configured. For the GT reference clock, it is decided by the onboard clock source. For Alveo card, the default clock source frequency is 161 MHz. For the GT reference clock selection, column used, and starting GT location setting, they can be omitted here and left at the default values. For the initial clock setting, we want to use the 100 MHz free running clock provided by the Alveo platform, so we set the number to 100 here. Please note, in the Shared Logic tab, we can choose to include the shared logic in core or Vivado example design. In the GitHub example design, we select to include them in core to simplify the design flow. If you need to use multiple Aurora IP instances in the design, you can choose to include the shared logic in the example design. This may save some resources for the commonly used logic. You can check the IB user guide for more details. In the core Aurora kernel design, we need an exit control slave to control the Aurora IP with native interface. Also need to monitor some status signals of the Aurora IP, such as PLL log status and the LAN up indicators. For the Aurora data stream, since the Aurora IP doesn't have the data buffer internally, also we need to convert the data stream from the Aurora IP clock domain to the platform embed clock domain. So we insert two data FIFO IPs here for TX and RX paths, respectively. Also, because the exit control slave uses the common platform exit clock as well, so some clock domain crossing primitives are inserted between the exit control slave and Aurora IP. After we have finished the Aurora kernel RTL design, we need to package it to the Vivado IP and finally convert it to the Vitis kernel file. The RTL kernel package steps are similar to ordinary RTL kernels, with some additional attentions to the Aurora IP relevant signals. First, we remove the auto-inferred initial clock signal here to avoid the incorrect clock signal collection in the later linking step. Second, we manually infer and bound the GT reference clock pins to differential clock interface. Third, we manually infer and bound the GT data pins to the GT differential data bus interface. These two steps can simplify the connection setting in later linking steps. Before we enter the linking step, we need to get the name of the ports and pins for Aurora IP connection. These ports and pins include those for GT reference clock, GT lanes data bus, and the initial clock. Using Alveo U200 card as an example, you can use the platform info command to get these informations, as the text highlighted in red. For other Alveo cards and target platforms, you could also find similar information for the signal connection purpose. We can also use Vivado GUI to find these ports or pins. We can use Vivado to open an existing linked project, which is automatically generated during the Vitis linking stage. We open the main user block design, whose name might be the ULP, and can find the ports and the pins corresponding to this text information we got in the previous page. Now we need to finish the integration, namely Vitis linking. The Vitis linking step is same as normal Alveo platform-based acceleration design. We just need to specify some additional connection for the Aurora IP. These three lines highlighted in red correspond to this additional setting: GT reference clock, GT data bus, and the initial clock. We use the platform signal names we got from the previous step in the linking configuration file. Once the Vitis linking job is finished, we can open the auto-generated Vivado project to verify that these special Aurora IP signals are connected correctly in the platform. In the example design, the Aurora kernel is implemented as a free-running RTL kernel. So we just use the normal user-managed kernel management APIs provided by the XIT to control the Aurora kernel. We will firstly declare the Aurora kernel as an XIT IP. Then we can use the register read and write data APIs to access the XE control slave directly. For the data stream control, since the Aurora kernel is an always running module, so we just use the normal XIT API to control the two HRS kernels, which act as data movers, so as to control the data stream flow. The host program will generate 100 megabytes random data by default, transfer them into the global memory, then send them to Aurora kernel via the XE stream interface. The received data from the Aurora kernel is compared with the original data. In the meantime, some important Aurora data signals are constantly observed. Finally, when all the data transfer is finished, the overall throughput statistics is given. Now we talk a little about implementing the 100 gigabits per second throughput Aurora link. To achieve this, first we need to set the line speed to 25 gigabits per second in the IP configuration dialog. This line speed clock value can be generated accurately by the PLL based on the default onboard reference clock source. The corresponding Aurora internal XE stream clock frequency is about 202 MHz now. Please note this frequency value exceeds the default 300 MHz default platform kernel clock. So if we reuse the design structure at the 40 gigabits per second case, there will be the performance bottleneck here as well as the data loss brought by the FIFO overflow here. To account for this problem, we can either use the higher platform kernel clock or increase the external XE stream data bus width. This block diagram depicts the latter method. It uses wide to narrow and narrow to wide XE stream data bus with converter IP to increase the external XE stream data bus to 512 bits. Hence, as low as the 201 MHz effective amber clock can satisfy the data throughput requirement. Here is the running result of the modified design for the 100 gigabits per second Aurora loopback test. We can find that the data transfer throughput statistics has achieved the 100 gigabit per second level. If you are using VCK5000 Versal development card, you can implement the Aurora protocol in similar way. We have prepared the same example design on VCK5000, and you can download it from the VCK5000 secure site. Please note, only the latest VCK5000 production version platform supports the GT kernel connection. So if you want to implement the Aurora interface on VCK5000, please use the production version card and download the latest platform from the secure site. VCK5000 has GTY transceiver and the QSFP28 interface as Alveo cards. Different from the Aurora IP in Alveo cards, on VCK5000, we recommend to generate the Aurora IP in a block design. This is because the generated Aurora IP will not include the GT transceivers, and you need to instantiate them manually in your RTL design. If the block design flow is used, the block automation will help you to finish the GT kernel instantiation and connection. The Aurora IP block design is generated as the flow here. First, create a Vivado project. Then create a top-level block design for Aurora model. Then add and configure the Aurora IP. Then run the block automation operation. Finally, create the ports and the necessary signals. When we got the final block design, we can just use it as a full Aurora IP with the same flow as the Alveo card case, including top-level Aurora kernel design, IP packaging, and the kernel file generation. Here shows the example Aurora IP block design on VCK5000 cards. You can find that it is similar to the generated Aurora IP in the Alveo case. 3 key Aurora signal ports are highlighted here, including the GT reference clock, GT data port, and the initial clock. The other signals can be connected to the axis stream data FIFOs or axis control slave in the top-level Aurora kernel design. With similar linking step, we can get the final hardware Excel bin files. We can use Vivado to open the auto-generated project and check that all the signals of the Aurora kernel have been connected correctly. The Vitis linking configuration for Aurora IP signals is listed here, which is very similar to the design on Alveo cards. Now we quickly go through the steps to implement Ethernet interface with GT kernels on Alveo cards. Ethernet is the mainstream Internet communication protocol. With GT kernels on Alveo, you can implement smart NIC and other various data center level applications. Again, an example design using the Ethernet IP is provided, and you can find it on the GitHub. Xilinx provides a full 10 gig and 25 gig high-speed Ethernet subsystem IP with charged license. Without the license, you are not able to generate the hardware bitstream file. Xilinx has provided mature high-speed Ethernet subsystem IP product to the users. Now let's recall that each Alveo card has 1 or 2 QSFP28 interface caches, and each QSFP cache supports 1 to 4 lanes. So the 10 gigabit Ethernet and the 25 gigabit Ethernet can be implemented on each lane of the QSFP28 port, and each QSFP port can support up to 40 gigabits per second or 100 gigabits per second Ethernet connection. Both fiber cable and copper cable are supported. Now please look at the example design. Just like the Aurora-based design, this Ethernet example design just implements a data loopback path with Ethernet IP, axis control slave, and data FIFO IPs. To implement a real Ethernet application is very complex, which is beyond the purpose of this webinar to illustrate the design flow. So what is different from the Aurora case? This example design is a dry design, which means it only demonstrates the Vitis integration flow and doesn't realize any meaningful functions. You could refer to relevant Ethernet IP documents for actual Ethernet design guidelines. Because the Ethernet IP system uses the same GT kernels as Aurora, so the design flow for Ethernet application is totally same as the Aurora case, which includes IP generation, supporting models and top-level RTL wrapper design, RTL kernel packaging, and hardware linking. For the Ethernet IP generation dialog, it is similar to the Aurora IP too. We need to set some key parameters here. GT reference clock, which is set to about 161 MHz. Lane speed can be set to 10 GHz or 25 GHz. Number of lanes or cores can be set to 1 to 4. And the GT free running clock, which can be set to 100 MHz, just like the initial clock in Aurora case. The top-level RTL wrapper for the Ethernet kernel includes access control slave and data FIFOs, just like what you have seen in the Aurora example design. The access stream data FIFO IPs are used here again to handle the data speed mismatch and isolate the two clock domains. The clock domain crossing primitives are also used here to isolate the Ethernet IP from the access control slave. The Ethernet kernel packaging step is also very similar to the Aurora case. We just need to pay attention to the GT kernel related signals. We will group the standalone pins for GT reference clock and the data bus into the predefined interfaces. By this way, the signal connection is simplified in the later linking stage. You can find more details in the GitHub repository. The Vitis linking step is totally same as the Aurora case. You just need to specifically connect the three Ethernet IP related ports, and other connections follows the standard Vitis usage. Similarly, we can use the Vivado to open the linked design to check that all the Ethernet specific signals are connected well. Now let's have a brief summary here. First, you can see that the integration of GT kernels on Alveo data center accelerator cards with Vitis is very simple. We just use the standard Vitis Flow with RTL kernel to finish this. The QSFP ports on Alveo card provide the external access to the GT kernels. With GT kernels on Alveo cards, you can implement both the Aurora protocol and the Ethernet protocol with material IP provided by Xilinx or AMD. Aurora IP realizes the lightweight inter-card data communication protocol, and it is free. Ethernet IP provides a full function interconnection possibility. For both Aurora and the Ethernet protocol, each QSFP28 port of the Alveo card can provide over 100 gigabits per second data throughput for each direction. Well, that's all for this webinar presentation. For the next steps, welcome to access the download page for the latest Vitis product release. Also, we encourage you to access our GitHub repository to get more Vitis Flow tutorials and example designs. Thank you for joining us.